This is an example of a proof by contradiction, and here we're going to show that every composite number n is divisible by a prime factor p less or equal to the square root of n. This is a very useful theorem when trying to find a factorization of a number n that we know it's composite, or to find a prime factorization of a number n. All we're going to use is the fact that every natural number bigger than 1 is divisible by at least one prime number. I'm going to prove this via contradiction, and whenever you are using contradiction in a proof, start by saying that you're going to use contradiction, and then assume that the theorem is false. So we're going to assume in this case that there is a composite number n such that every prime divisor of n is bigger than the square root of n, and then we will proceed logically until we reach some nonsense, which will mean that our assumption must be false. First, since n is composite, we can factor it as n equals a times b, where a and b are non-trivial factors, so both are between 1 and n. Now, those numbers a and b are natural numbers bigger than 1, so by our fact, those have a prime divisor of their own. So there's a prime divisor that divides a, which in turn divides n, and a prime divisor of b, which in turn divides n. So I'm going to call those p, a prime divisor of a prime divisor of q, which are also prime factors of n. And then by our assumption, which eventually will show it's wrong, by our assumption, those two prime divisors of n have to be bigger than the square root of n. Hence, n is a times b, that's the factorization of n, and a has a prime divisor p, so a is at least p, and b has a prime divisor q, so b is at least q, so a times b is bigger or equal to p times q, and now we know by our assumption that p is bigger than the square root of n, q is bigger than the square root of n, so p times q is bigger than the square root of n times the square root of n, but that is n. So we get that n is bigger than n is bigger than n. That's clearly a contradiction, so we've reached the nonsense we were looking for. That's our original assumption, the assumption that every prime divisor is bigger than the square root of n must be false, and therefore there is one prime divisor of n that is less or equal to the square root of n, and that's the end of the proof.